Yes, please, I can hear you.
Okay, okay. Uh, are you joining for the first time? Like this
Yeah, yes, yes,
session?
please, yes. Yeah.
Okay,
But I've been submitting the assignments regularly. Yeah.
okay, that's good. Okay, Rangarajan, can you introduce yourself? Like that will be good.
Yeah, I'm
For
I'm actually 64 years old, and I'm doing this like after my PhD, which was in low energy cooling,
okay,
and I'm trying to work on the field of microclimate management. That means, in hot places, creating uh, creating outdoors and indoors with more acceptable microclimates, and the use of water, the storage and harnessing water is a very important resource for that. So I found this course very interesting and useful for that.
good.
So I'm trying to build models for microclimate, and I find some of them, even like what we did earlier in evaporation and all, the models are similar.
Okay,
Uh,
okay. So which model you were using?
that the log wind profile model, which is used for momentum. We use actually the diffusivity constant and the diffusion equation, right, to model uh, the vertical flux. So
Okay,
one is about wind speeds, the other one is to use heat, where we say that kh is equal to km, and so, like, if you're standing on the ground,
okay,
and if there's radiation, so we cut radiation by using plants and trees and all that. But suppose you're standing on the ground, how hot will you feel
okay,
from radiation, from convection, uh, things like that. It's a bit complex for me now, but I'm just slowly building, trying to understand and build that. Like,
okay,
so then once you know what it is, then you can use techniques, like today you can even use internet of things, like, with sensors, so that you can create and come within the comfort zone in terms of parameters, in terms of air temperature, humidity, wind speed, and things like that. Like,
okay. That's good.
yeah.
Okay, I will be waiting for a few minutes. Then
Sure, 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 please. Yeah. I'm muting my.
yeah. Ashish, how are you?
I'm good. I'm good. Hello.
Okay, nice to see you again.
Yeah. Thank you. Thank you.
Okay. Ashish, have you searched that data that you were looking for in our previous session?
Yes. 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 Yes.
So, any input you got from there?
We got the river data and all data which we required.
Okay, that's good. I will start the session by 6:15. Okay.
Okay.
Okay, so before starting the session, I want to mention few points. Like this session will account a discussion related to numericals along with some theoretical concepts. So I want both of you to engage with me so that we will discuss simultaneously while looking at the question. Okay.
Okay. Okay. Sure.
Okay, so welcome to the next session on assignment number 4 regarding engineering hydrology NPTEL course. So myself Prabhat Dwivedi, I'm a PMRF research fellow working in the Department of Hydrology IIT Roorkee. So in today's discussion we will be covering the topics which are as follows. Like in the first, I will be showing some of the observatory instruments that are here in our department at IIT Roorkee. Then we will continue our discussion in evaporation. What are the methods that are related for computing the evaporation magnitude? Then what we understand by evapotranspiration and what are their methods and what are their significance while we are dealing with the hydrological cycle. So at first I want to just summarize, I want to just make you aware of the instruments that we have studied earlier. So here you can see in the first picture you are looking at the recording type siphon rain gauge. Today only I took this picture and I added into this slide for better understanding that like in our previous lectures we have only seen its schematic diagram only, but how this instrument look like. So here you can see a recording type siphon rain gauge where if we take out the external covering, the instrument will look like as it is shown in the second picture. You can see there is a graph attached and how the pen linked with the lever arm, it is floating whenever the water is getting accumulated or it is getting emptied. Wait a minute, maybe someone is joining. Okay. Okay, welcome Bala Murugan in this session. Okay, so you may be clear with what we are recording in the when we are dealing with the siphon rain gauge. Now the second picture that you are seeing, this one, it is of non-recording type Simon gauge. We usually take the reading at 8:30 am. We already go through this. And how is it look like? So there is a bottle inside this instrument which is continuously recording the rainfall for entire 24 hours in a day. And then at the end we are just transferring this water into some measuring flask and we are looking at how much depth of rainfall have been occurred in this near this rain gauge station. Now in further like in today's discussion we will be mainly dealing with the evaporation part, so I have just added a few pictures related to this. So there is one picture, it is showing class A evaporation pan. So you can see in the observatory there is a some circular kind of drum is there, which is storing some certain amount of water we are adding into it, and based on the heat energy that is coming at daily scale interval, how much water is getting evaporated we can quantify into it. We will further look into the, while we are solving the some numerical part, we will be looking into this. So at the next you can see Colorado sunken evaporation pan. So it is also one of the method where we are computing the evaporation value in the field itself. Then there is one more picture, it is showing that there is a automatic sensor based evaporation pan. So there is certain kind of sensor which is already immersed in this water, water which is kept in this pan, and how the water depth in this pan is fluctuating, it is getting recorded in this kind of electronic system, and this data is automatically transferring into our main storing device which is operating in our main office, head office. So before continuing to our discussion in the evaporation part, I want to mention one question that is related to our previous session, that is for computing the missing rainfall. So I want everyone to try to solve this question. So what is mentioned in this question and what is it has been asked in this? So you can see it is asking that we have to compute the missing rainfall of an inoperative station. So from the table you can see there are total 5 of stations which are kept in any catchment, we can say. So A1 is one rain gauge, there is A2, there could be A3 as well, A4, there is A5. Now what is the problem? So problem is like that this station, A4 station, is not working. It is not working, and it is we don't have the data yet, but still for the entire catchment we are continuously recording the data for previous year. So definitely for if we are having the data for previous record, so we will be having the normal annual rainfall. So normal annual rainfall is just a average value of past 30 year of data. So we have this data, and now we want to compute the average rainfall in the particular year. So here A4 is missing, so we have to compute this. So I want everyone to participate in this, and can anyone tell that how we can proceed in this? Like what will could be the concept that how we can try to compute this average rainfall if we don't have
Yeah.
record in this particular year.
We have to use the normal rainfall method formula.
Okay, that's good. Okay,
Yeah.
fantastic. So
The
normal ratio method, right?
normal ratio method.
Good. So can you also tell that there could be certain condition, like we also know that there is alternative method for this, that arithmetic mean method is also there.
If the value is deviating more than 10%, then we have to go for the normal ratio method.
Yes, that's good. So Ashish, you are right that we have to proceed after computing the deviation, that how much error is accumulating between the two rain gauges. So now I will be moving to the next slide, and you can see the data. So Ashish, just for everyone, don't go with the answer, okay? Yeah, surely we know that this answer will be coming, but the thing is, like, if we are computing here itself, that will be giving more insight into this, okay? So firstly, if we are looking for the missing rainfall, so here A4 is missing, so P of A4, it will be having a ratio of normal at that station A4, and then how much remaining rain gauge station which are there we have to compute. Right, Ashish? Am I right?
Yes. 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 Correct.
Okay. So try to figure out the value that are you getting this or not, so that we should proceed ahead.
Just give me 1 minute.
Yeah. Rangarajan sir, are you here?
Yes, I'm here. I put that in the assignment. I'm trying to find that in the notebook. Suddenly jumping into it, like whatever notes I wrote on the lectures.
Okay, okay, okay. Balamurgan, are you solving this? Okay, good to see. Tell me whether you are getting this or not, because uh, at the end of this course you will be having a certain kind of exam where you will have this type of question directly and you have to answer them. So it will be good that you are solving in parallel with me.
I am getting 25.130.
Ashish, have you computed that deviation? Like in this you can directly seeing the answer, right? I have not gone through computing the deviation, that how much error is existing between the missing rainfall value at A4 station with respect to other, like with respect to other in the sense A1, A2, A3, A5. Should I write that or not?
No need. I will calculate it.
Okay, for Rangarajan sir, I'm just writing one thing, that
Yeah.
if we want to compute percentage error existing
Yeah.
in the target rain gauge station. Okay, so our target rain gauge station is A4.
Right.
So firstly we have to look into the percentage error existing. If the percentage error is less than 10%, if it is less than 10%, so we will be following the formula. We can easily follow the formula, that is arithmetic mean method.
Yeah. Sorry, just one doubt.
Yeah.
There is a formula which says that the estimated value of that rainfall,
Okay.
yeah, which is equal to nx. That means that is the normal rainfall for that station, for which we don't have the reading
Right.
now, and then we have 1 by n sigma pi by ni, right?
Yes. Right.
So I just use that formula directly.
Right.
Now I didn't understand this bit about percentage error, calculating percentage error. That
Yeah.
part, because I just use this formula directly and get the missing rainfall. I mean, the rainfall for the missing station, the estimate.
Yeah, you are right, sir. So
Yeah.
basically, while we are in the field, there
Yeah.
may be a chance that maybe there may be a field disturbance due to which we are not getting the data, right? Or maybe
Okay.
there are certain chances where there is like a large amount of deviation may be there with respect to other, like
Okay.
so that is the target. So we are looking into the percentage error. So
Yeah.
if we are having any kind, like if we are having a catchment and we know that here stations are distributed like this: A1,
Mm.
A2, A3, A4,
Yeah.
A5, and
Yeah.
I'm just assuming that this area is having area of catchment of about 100 kilometers square, okay, or maybe less than
Okay.
this. So
Okay.
definitely the values may not be deviating in that way that we are not getting a like smoothness in this data. So
Okay.
A1, whatever the error we are getting between A1 and A2, it should not be going beyond maybe that is a standard one that I'm taking here, that is a 10%, but error
Okay.
should be less than this, then only
Okay.
data makes sense. Otherwise we are not getting like accurate data. If we are having data with a percentage error greater than 10%, then that is of no use, right? So we
Okay.
have to keep in mind before trying to computing like we are computing for the missing rainfall. So what I'm
Okay.
just saying that we have to go for percentage error existing in this. So
Okay. Hmm.
wait a minute, just I want to.
Okay. The answer is 11.2. I am getting 11.2.
Ha, that's good. But for Rangarajan sir, I'm just
Yeah.
showing you one question,
Sure, sure.
so there
Yeah.
you can get the more understanding into it. Okay, wait a
Okay.
minute.
So I have calculated it. That is 112 minus 85. It's getting 24%.
Yeah, that's good. Good. Okay.
Yeah.
So Rangarajan sir, you can see this question.
Yeah.
So here the question is like the same what we are discussing right now. So the here the same question is here. The normal annual precipitation of 5 rain gauge station, that is PQRS, is given.
Yeah.
Now there is one thing that rainfall is getting missing at station T. It is
Hmm.
asking that we have to
Yeah.
compute the rainfall, missing rainfall at station T. So now
Okay.
how we are proceeding into it?
Yeah.
So you can see, firstly, we already know that what is meant by normal annual rainfall. So it is just
Yeah.
average value of 30-year rainfall
Yeah.
record that we have in the
Yeah.
past.
Right.
Now there is an application like the condition that I am just discussing is
Yeah.
that the normal annual precipitation at various station, it should be less than 10% of the normal annual precipitation at X. So then
You mean the
only
variation would be less than 10% is what you're saying, or the absolute value itself? Like
it's a variation. It's a
variation.
like
Sorry.
yes,
Yeah.
yes.
Yeah.
So
Okay. Understood.
percentage variation
Yeah.
will be there. So
Hmm.
firstly we are looking into it. If it is less than 10%, then directly we can use this formula. But if
Hmm.
we are getting the percentage deviation greater
Hmm.
than 10%
Yeah.
for the same normal annual precipitation, then we
Yeah.
have to use this normal ratio method. Now
Okay. Hmm.
look into this question.
Yeah.
So we are having normal annual precipitation for the station P, Q, R, S, T. Similarly, we have the actual rainfall value recorded in the rain gauge for
Hmm.
P, Q, R, S, but T1 is missing. Now
Missing.
how we
Yeah.
are computing the variation?
Yeah.
So variation with other gauge. So our
Hmm.
target our target station is what? That is a T, right?
Hmm.
So we will
Yeah.
be looking the variation of T with respect to other stations. Okay?
Using the normal data, correct?
Yes, right,
Yeah.
right, yes.
Yeah.
So you
Okay.
can
Okay.
see now n of Tp. So what is
Hmm.
it is showing that we are looking for the variation at the like between the station T and P. We are looking into
Okay.
it. So you can see that this is a just a simple calculation that we are looking. So n of just n of T minus n of P divided by n of
Yeah. I understand that. Yeah.
P into
Okay.
100. So
Yeah. Yeah.
we are getting the value of 8.76%. So
Hmm.
there is a deviation. You can say deviation will be definitely it will be a error. Okay, it will be
Yeah.
error in the recorded data. So
Yeah.
similarly, for the T and Q station you can compute. So we are getting how much? We are getting 25, approximately
Yeah.
26%, right?
Hmm.
Similarly, for the T and R, we are getting the value of about 44%. Similarly,
Okay.
for T and S, we are getting 25%.
Right.
Now, what is the thing? That if we are computing, we are getting the variation, and if
Hmm.
any of the variation is getting greater than 10%, then we
And
have to
yeah.
use this formula.
Yeah.
So
Sir,
now,
just
yeah,
physically, why
yeah.
does this happen? Is because there could be a orographic rainfall happening somewhere within that catchment itself, uh, because of this wide variation of, let's say, 100 kilometers square within
Yes,
100 kilometers square.
right.
Is it because of the terrain might be different, or within the same catchment, or
Yes, of course, it could be. It could be
okay,
like due to a terrain, but
okay,
mostly what we used to say that we record this data by ourselves, right?
okay,
There are in our India we usually prefer a recording type rain gauge, and we have to we have to record the data not in electronic mean, but we have to take the manual reading.
oh,
So
okay,
there are
okay,
more chances that
hmm,
there is a human error involved in this while we are
okay,
dealing with this. So
okay,
yes, of course, you are right that natural factors are also the we are
hmm,
accounting, but
hmm.
simultaneously human factors should also be considered in this.
Okay,
Okay.
because in normal rainfall, as an average over 30 years,
Yeah.
the manual error would have been averaged out to some extent,
Yes.
right?
Right.
Yeah.
Right. Right. You are right. Yes.
Okay.
So
Thank you.
definitely,
Thank
yeah.
you.
Yeah.
Yeah.
So I'm moving to the our main discussion.
Sorry. Yes, please.
Yeah.
So I could see the difference. Yeah. Right. Thank you.
Okay. So is everyone getting the answer? Like it should be approximately 11 centimeters something.
Yeah, I got it 11.2.
Okay. Balamurgan got his. Okay, that's good. Okay, missing value. Nice to see Balamurgan. You are actively involved. Okay, I'm moving ahead. So there is a next question related to the evaporation. So here the question asking is the chemical that is suitable for reducing the evaporation rate.
I saw this. I googled this. It's cetyl alcohol.
Yeah, of course. Yes, you
Yeah.
are right, sir.
Yeah.
So there is always a just kind of, if we are having a large kind of reservoir, if it is there, and we want to just want to reduce, we can't stop. Yes, of course. So we can only reduce. So just this hydrocarbon, this is a cetyl alcohol is just an hydrocarbon
Okay.
which get spread over the surface of the water, and it cut the absorbance of heat, and so that water vapors from the water, it is not going outside from this. Okay.
So the boiling point of this will be even higher than the boiling point of water, so that this alcohol doesn't evaporate away.
Yes,
Like,
you are right.
okay,
Yes, yes,
okay,
right.
okay.
So just a few comments on this. So you can see cetyl alcohol is found to be, sorry, wait a minute. Okay. Okay. So it is a suitable chemical for reducing the evaporation rate. So this is a white waxy crystalline solid which is in the form of lumps, flakes or powder. So we are adding this into the directly into the water surface. It is applying into the water surface in the form of powder, emulsion or solution in mineral turpentine. It is just a kind of mixture. Now the next
First time
question.
I'm
Yeah.
seeing alcohol in the form of a solid. Like, so that's really interesting. Uh,
Actually, just it is saying, yeah, yeah, you are right. But
hmm.
the thing is, there is a certain kind of chemical they are adding, and it's just like of admixture. It is okay,
Oh,
and
okay,
it is
okay, okay,
finally converted into some form of powder.
okay. Understood.
Okay, yeah.
Yeah, fine.
So next question is, Lysimeter is used to measure. So maybe in the discussion you might have heard of this lysimeter.
Yes. Yes.
Evapotranspiration. Yeah.
Evapotranspiration.
Yeah, that's good. Okay. So this is evapotranspiration. So can you tell me that what is actually mean by evapotranspiration? That what we do we understand by this?
Uh,
If- Yeah, please go ahead, please.
the transpiration of the evaporation of through the ground surface, including the from the plant leaves.
Yes, you are right. So if we are having any kind of canopy is there in the plant, there are leaves, so definitely evaporation will be taking place from here. Okay, so we are calling it as transpiration process. Okay, and simultaneously evaporation, whatever the moisture it is there in the subsurface part, so based on the heat energy or maybe a flux which is coming, heat flux is coming, so definitely there may be a net radiation working on it, and some water moisture it will be working. Okay, it may be getting evaporated, so we are calling it as a evaporation part. So integration of both the things, evaporation as well as the transpiration, we are calling it as evapotranspiration. Okay, should I move ahead?
Yes,
Yes.
yes, please.
Yeah, so there is a few comments in this, so I'm just adding into quickly. So lysimeter is an experimental method, you have to note it down. This is an experimental method to measure the amount of actual evapotranspiration that is released by the plants, usually crops or trees. Now what we are actually doing, like there is how we are proceeding into this. So you can see there is a certain kind of setup we have to make, as just we discussed that this is an experimental method. So in the field itself we have to make some certain kind of setup. So this setup is basically like we are dealing with in a subsurface layer, we can say, underground. Okay, inside beneath the ground we are constructing a setup. Okay, so this entire setup is there, and then whatever the ET value we are measuring, we will be measuring by applying some kind of data logger, that is a sensor we are inserting at some different depths, we can say. Okay, from the top there may be different depths, like you can say there is a D1, then other one will be at the D2. So at different depths sensor will be installed and we are getting the value. So you can see watertight tank containing the soil, that this is a requirement for building this. Now we have to set up this where plants are growing, and at the same time it should be present in the surrounding field as well, like it is talking about the plants that is there. ET is estimated in terms of amount of water required to maintain constant moisture condition within the tank. So it is computing based on the moisture condition, we can say. Okay,
Why are we using a weighing balance if we can't do this measurement only on volume measurement alone?
okay, so weighing balance may be just because we are concerned with the moisture part, right? So definitely once if we are having the porous media, definitely moisture, if we are having a moisture in the porous media, definitely there may be certain kind of weight. Okay,
Okay,
I
okay,
can say
yeah,
W1, but once this transpiration and evaporation process is happening simultaneously, definitely
yeah,
moisture content will be going like it will be reducing continuously.
correct,
Okay,
correct,
so
sir.
we
Yeah,
should be having some kind of difference between W1
okay,
and W2. So it will
correct.
be adding just a kind of a cross check for whatever the data we are getting directly from the sensor.
Okay, okay, thanks.
Yeah.
Understood. Yeah.
So now the questions come. It is related to again evaporation. So there is a question. It is asking that we have to compute the volume of water evaporated in a month. Month in the sense that is 30 days. Now look
Yeah.
at the question. So question it is saying that we are having a canal, okay, and this canal, how much length we are taking? We are considering only up to 80 kilometers of length. Also,
Yeah.
whatever the water surface it is there at this stretch, it is saying that entire area of this stretch, it is yes, area is missing, I guess. Okay, they are saying about the width, so definitely we will be having a width. So W is here 15 meter, so we can directly get the area. Yes, we know that this will be a rectangular shape, okay, in general. So we can compute this area L by B, we can easily get. It will be having a unit of meter square, I can say, because we are converting it directly into 80 into 10 to the power 3 in meters. Okay, now what they are doing, so near this canal they are having a class A pan. Okay, just I show you the picture. Okay, so
Yeah.
class A pan they have installed, and now what they are getting, so they are getting the pan evaporation value. They are getting certain kind of pan evaporation, and how much they are getting? They are getting 0.5 centimeter per day. They are getting this value. Now,
Yeah.
now they want to know that how much volume of water have been evaporated from this entire water surface. They want to know this. So we want to calculate volume of water lost from the target area, I can say.
So we can assume this is a ISI pan or something to get
Yes,
the
yes,
pan
yes, you
coefficient.
can. Yeah, definitely. Then
Yeah.
only you have to see certain kind of correction we have to apply, na? Because
Yeah.
pan evaporation is just a kind of reference value we are getting. Not
Correct.
it is
Correct.
not an actual value.
Correct. Yeah.
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 So can anyone approach, like can anyone tell that what could be the approach, how we can proceed and we can compute this?
So it is showing zero point 0.5 centimeters per day in the pan.
Yes.
So using that and also using the area of the canal
Yes.
multiplied by the pan coefficient,
Right.
that should give us the total volume per day. If it be using zero point 0.5 centimeters per day, then we multiply it for 30 days. Yeah.
Yes. That's
Yeah.
good, sir. You are right. Ashish, do you have any points to add in this?
Not yet.
Okay, so whatever the Rangarajan sir is telling, are you supporting him? You are agree with him or not?
Yes.
Okay, so what he is saying that if we want to compute the volume, so definitely one way is to get directly that definitely volume will be having a reading of some unit. It will be in meter cube or maybe in liters. So yes, volume will be like whatever the area we have, and then how much depth of water is getting evaporated. So depth of water evaporated. So right now we have a pan evaporation, right? So from using this, we have to compute the depth of evaporation, that how much water have been evaporated, actually evaporated. So for this, we have to multiply the coefficient Cp. Okay, said that this is a pan coefficient. So pan coefficient will be multiplied by the E value that we are getting directly from here. Okay, so for ISI pan, usually what value we are taking? We are taking the value in the range of 0.7 to 0.8 in India. Okay,
Yeah.
so we can take any value. So for time being, I will suggest to use 0.7 as the value and go for it and compute the value.
Okay.
So now you can see directly that we are having the data, that is pan evaporation measured per day. We are having this data, and then we have the canal stretch of 80 kilometers. Then average surface width is also here, and then we have pan coefficient. Now look at this this concept that it is what Rangarajan sir just mentioned, that if we want to compute the volume of water which have been evaporated from the region, so we have to multiply the area, that is a surface water area, with the actual depth of evaporation. So now compute and get this value. Are you like among the 4 options, what option you are getting? This would be interesting to know.
0.005 into.
Let me check. Bala Murugan. Okay.
Into 0.7.
Okay, Bala Murugan. Ha, yes, you are right. Pan coefficient, how 0.7. Okay, so basically 0.7 in the sense that while we are dealing with the ISI standard class A pan, so based on the experimental which have been done using this instrument across India, so they have come up with the range 0.7 to 0.8. So definitely if there is a specified location we are dealing, like for Rajasthan, maybe Gujarat, or maybe in Uttarakhand, these values may be varying definitely, but this is just an average value, because we are mainly concerned in like finding out the strategy.
Just a question, sir. This
Yeah.
pan factor
Right.
is really, I mean, from what we read in the lecture and the textbook,
Yeah.
it has really no link with the season or the location, right?
Yes. Yes.
Because,
Yes.
but on the other hand, you were just saying, in if it is in Rajasthan, the pan coefficient might be different.
Yes, the thing what I am just saying is that
Yeah.
you know that if we are talking about the class A pan, so
Yeah.
you are knowing that this entire class A pan is made of certain kind of material, right? So material is
Okay.
what? So it is a metal, right?
Hmm.
So once the heating is here, once the heating is coming, heat energy is coming into this,
Yeah.
definitely like along with the water, this matter body will also be getting heated up, right? And
Right.
you know
Correct.
that there could be a change, I guess, in a change in the sense what, like it may be getting expanded, right? This
Yeah.
metal body is getting expanded due to
Right.
excessive heat. So I am just saying that if we are in the Rajasthan, definitely heat energy will be
Okay.
more,
Okay.
right,
Yeah.
as compared to
Okay.
other
Okay.
region. So based
Yeah.
on this, we have to apply some correction, and we will be getting this.
Okay. So, in my understanding, right, it depends on the macroclimatic conditions of the place. That is,
Exactly. Yes.
yeah.
Yes.
Okay.
Right.
Just a observation, general observation is looking at in cubic meter. A cubic meter itself is a very big measure.
Yes.
180,000 cubic meter water is lost just like that. Is also something we have to learn how to manage our water resource, right?
Yes, 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 right, right.
Yeah.
That's why people who are working in the wetland areas, they are mainly concerned about this evapotranspiration
Uh,
parameter. They
okay.
usually more concerned in this.
Okay.
Yeah.
Okay.
So anyone getting the answer?
Yeah, 126,000.
That's good. Good. Can you, Ashish? Can you tell me Bala Murugan got the answer or not?
Yeah, he got also D.
Okay, okay. Uh, Rangarajan sir, like what is your answer? Are you getting, or
No,
are
I'm
you
sorry,
still
sir.
solving?
Today I'm not prepared fully. Next time onwards, I'll join
Hello?
with my calculator. And
That's good. That's
yeah,
good.
I'm
Not an
sorry.
issue.
Yeah.
Just from the explanation, you may be getting that how we how we are approaching to this problem, right?
Yeah, sure, sir.
Yeah.
Sure.
Okay. So the next question is, you can see it is asking about the factors. Okay, so factors which are affecting directly the evaporation process. So how the variation it is asking that both the factors, like factors should be having a increasing influence in the evaporation process, like evaporation increase with this with an increase in the factor, it is asking in this style. So you have to see the options, and in the similar manner you have to reply that what are the factors which may increase the evaporation with increase of their magnitude.
So
Air
I
and
would think it
wind
is
speed.
number 3 and 4. So 3 and 4.
Yes, you are right.
Uh,
Air
And
and water temperature. Yes, Ashish, you are adding something?
no, 3 and 4 is right answer.
Ah, that's good. Good. Yes. So, depth of water is having inverse relation. Similarly, atmospheric pressure is also having inverse relation. So, just for your just further information, I just added a few points that if we are having more heat energy, so latent heat of vaporization will be more. So, as you already got the answer, so I should skip this. Okay.
Mhm.
Yeah. So the next question is, which of the following is not a standard evaporation estimation method? So it
I would
is,
say the mass balance method, sir, because
yes,
yeah.
right. So you are right. Ashish, anything to add?
Yeah, mass balance method is correct one.
Okay, yeah, that's good. So you are right. So aerodynamic method, energy balance method, Priestley-Taylor method. So they all are an part of analytical evaporation method. We are computing analytically. Okay. Mass balance method we can also do. We can also compute evaporation, but there is certain kind of additional information we need. How I'm just saying this, because you know that mass balance method is just a input, whatever the input we are giving minus output, okay, and it is
Yeah.
directly giving you a storage value, right?
Yeah.
But what
Correct.
the thing I'm just mentioning, output, you are just you are aware of this, that yes, definitely evaporation will be a part of output, right?
Yeah.
Yes.
Mhm.
And then similarly there may be certain parameters we are which are just indicating the input part. So precipitation may be one of them. Then again, if we are talking about infiltration, then it is also getting as an input part, right? And there could be some kind of extraction we are dealing, like if we are just spilling out some amount of water, so that will also be counted in the output part, right? But at the
Yeah.
same time storage will also be there. In
Yeah.
that if we are considering any kind of hydrologic system, okay, so there is some kind of inflow is coming and there is some kind of outflow going from the system, so definitely there will be a storage. Is anyone joining? Are you getting something?
No, no, no.
I guess yes. Okay. Okay. So now you got it that we can also compute the ET like this evaporation E value from mass balance method also, but it should be provided with some additional information of other parameters. Like if we have the precipitation value, if we are knowing the P value at this at the particular region, we are also having the infiltration values. We are also knowing that how much water is getting withdrawal from that region. We can directly compute E value, right?
Yeah.
Yes.
Yes.
So for your information, I just added this slide that what are the like what are the methods of estimating the evaporation. So we have three major methods. So we can compute it by experimentally. We can approach experimental equations. We can also follow the analytical method. Sorry for the confusion. I guess it is getting reversed. Okay, don't messed up with this,
Mhm.
because it should be an analytical and this should be an empirical.
Sure.
Okay. Yeah.
And also the other three analytical methods are, you compute based on measurement of climatic variables, right? Either
Yes,
the
right.
temperature. Well, in
Yes.
the mass balance method, like you said, you need to measure other physical things like infiltration and all other things.
Yes.
Yeah. Okay.
So in that case, what we need other parameters directly measure in the field.
Yeah.
Okay,
Correct.
we
Yeah.
need help of other hydrological variables. But for
Yeah.
this case, if we are knowing certain kind of meteorological parameters,
Yeah.
like for this case, if we are knowing radiation value, right? Heat
Yeah.
energy, how much heat energy is coming, how much wind speed we have. So we
Yeah.
can, using this, we can directly compute this,
So
right?
with a weather station, we can compute
Yeah.
using a local weather station. We should be
Yes.
able to compute that.
Right, sir.
Yeah.
Right.
Yeah.
Yeah. Okay. Now continuing to this, so you can see a question. So it is asking that we have to quantify the contribution of wind velocity gradient and the specific humidity gradient in terms of percentage of heat energy. So you can see that it is directly mentioning that it is related to combined method of evaporation estimation. So
Yeah.
you might have heard that the same thing that just is mentioned here, analytical method, third one, combined aerodynamic and energy balance method. Okay, so here what are the major methods that are like what we come up with? So here two major methods are operating in this. So we are getting the Priestley-Taylor method, okay, using
Yeah.
this principle, aerodynamic and energy balance. And similarly we can also achieve up to Penman-Montet. This Penman-Montet method is basically useful for computing the ET, okay,
Right.
but this Priestley and Taylor we are getting the E value. So now what it is saying, it is saying that among the total evaporation value, we are computing evaporation from, first one is energy, right? Energy mass
Yeah.
balance we are computing, plus energy which evaporation which have been computed using the aerodynamic method. Okay,
Yeah.
so now it is asking, so like I want to ask one thing, can you tell that what are the mentioned parameters? There are mainly three parameters you can see from this question, right? What are the parameters? It is asking wind velocity gradient, okay, then the second one is, you can see, specific humidity it is asking, and then third one is heat energy. So can you tell me that which parameter is associating with which kind of method? If I talk about heat energy, so it is related to which method? Can you tell?
That is heat. That's the heat balance method. It's basically based on the radiation, net radiation.
Yes, you are
Right.
right.
Yeah.
So this is an energy balance method, right?
Yeah.
And then if I talk about the wind velocity gradient and humidity, so it
That's the
is,
aerodynamic
yes, you are
method.
right.
Yeah.
Yes. So now the question is asking that the contribution, that how much it is contributed, like what is the contribution of this, maybe in percentage I can say, for an example, it may be having 20% contribution in an overall evaporation in the region.
It's around
Okay.
30%. So the aerodynamic method
Yes.
contributes about 30% of the heat energy method, not the total thing, but 30% of the heat energy method. Right.
Fantastic, that's good.
Yeah.
So you are right that whenever we are applying this combined method of evaporation in the large catchment, okay, keep in mind that we are seeing into an large catchment region, okay. So if we are
Yeah.
having large catchment area, because this experiment, whatever the value we are looking into it, that 30%, yeah, definitely. So basically this energy balance, it is contributing 100%, then this aerodynamic method is contributing how much, 30%. So in
30%.
total
Yeah.
it is contributing overall 130%. So you might have come up with one of your that is a one variable you might have come up in your lectures, that alpha value have been taken 1.3.
1.3. Yeah. Right.
Yes,
Yeah.
so this is because of that only. So it is just saying, so how how they have got this, how they have got the this 30% and 100%. So they have tested this particular combined method for the large catchment, and they got the result that 100% of evaporation is have been noticed from using the energy balance method as compared to aerodynamic.
Okay.
Yeah. So
Okay.
for your information, I have just added a slide. You can see that combined evaporation equation can be written like it is mentioned in this in this form. You can see. So you can directly see that ER is there. So ER is just
Right.
representing the rate of evaporation
Net.
by energy
Yeah.
balance method, and
Correct.
then simultaneously EA you can see. So it is just a part of aerodynamic model. At the same time, I also just mentioned that what are the parameters it is associated. So you can see energy balance method, heat energy is required. Simultaneously, aerodynamic method, humidity and wind velocity is the input parameter. Without this, we
Right.
can't approach for this. Okay.
Right.
Yeah. Now, see the question. I'm happy that one discussion was based on this only, that pan factor used in the pan evaporation method is dependent on, right? Just
Mm.
in the previous discussion we already discussed this, right?
Yeah.
Can you tell that what could
So
be?
my
Right.
understanding it is none of these, because that's why I requested you. Just asked you whether it's more the climatic variable or the location. It is not definitely location as latitude or longitude,
Yeah,
and
definitely.
definitely it is not the season. So my answer would be none. So
Uh, okay.
yeah,
In continuation to this, I just want to recall that thing that I just mentioned, that within India,
yeah,
pan evaporation coefficient, that is CP. Okay,
yeah,
it is
yeah.
asking for the pan factor, right? So CP is the pan
Correct.
factor. So I
Yeah,
just mentioned that if we are here in the Rajasthan, right?
correct.
So definitely there is, if we talk about the climate, so temperature is usually high in those regions, right?
Correct. In
Yeah,
summer, yeah, for sure. Yeah.
exactly. I'm talking about the
Mm.
summer only. But
Yeah.
if we talk about other regions, like
Mm.
maybe Madhya Pradesh, or maybe in the southern region, right? Maybe
Yeah.
in Karnataka, nearby Karnataka or lower part of Maharashtra, I can say.
Yeah.
So you can see some kind of normal temperature ranging from
Yeah.
maybe 35 to 40 only. Okay, but
Okay.
here you
Okay.
can see at the same time you will be witnessing temperature of about maybe 43 or 44, something like that.
Correct.
So now you can see that if we are installing the our location, sorry, our evaporation pan in this
Mm.
in both the regions. Okay, so
Mm.
I just mentioned that this entire body is made of metal, right?
Correct.
Here also and here also. Now can
Yeah.
you say that where the deviation will be more? You know that
Yeah.
metal, if we are heating the metal, it is
Yeah.
getting expanded, right? So maybe
Correct.
it is
Mm.
getting a shape like this. Okay,
Mm.
so we need some kind of correction, right? So CP is
Correct.
required. Okay,
Okay. Understood. Understood.
so here the thing is, we are also talking about the temperature. Okay, we are also
Mm.
talking about the time, like maybe temperature. Yes, you of course, Rangarajan sir, you just mentioned na, that
Yeah.
season, right? So we are talking about the summer season.
Yeah.
So season also accounted, and now again the Rajasthan and other location I'm talking, so definitely it is talking about the location, right?
Yeah. Okay.
So
In
we
that
got
sense,
both
I
the things.
agree. I agree, sir.
Yeah,
My understanding was when you say location, it's like lat long of a place, latitude, longitude.
yeah,
But I understand
uh,
your logic now.
okay,
Certainly. Yeah.
okay,
Yeah.
that's good. Ashish, are you getting this?
Yes, I got it.
Okay, can you tell me about status about the Bala
Location.
Murugan?
He not yet replied, but he is
Okay,
replying.
okay, got it.
So then the season also plays a part, right? So both season and the location should play a part, right?
Yes, yes, you're
Yeah.
right, sir. Yeah,
Yeah. Okay. Yeah. So it is both. Yeah.
right, right. So for your information, you can see metallic pan sites, or maybe they may get enlarged whenever the evaporation, actual evaporation, it may disturb the values what we are trying to focus.
This is a new information. Very good. Thank
Yeah.
you. Thank you.
Okay. Good. Now you can see there is one more question related to reference crop evapotranspiration. Okay. So now
Yeah.
it is asking about, like, it is mainly related to crop only. Okay.
Hmm.
So we are having a certain kind of maybe ground where we are just having plants in the region. Okay.
Yeah.
And for that case, it is saying that we are getting the reference crop evapotranspiration. So before getting into a deeper discussion, I want to just know that what you understand by reference crop evapotranspiration.
So
Actually,
it's about using a standard crop like grass of a certain height,
Yeah.
maybe 8 centimeter to 15 centimeters
Yes,
over
of
an
course.
area, and you measure the evapotranspiration there. In that, that
Right.
is a ETO, right?
Yes, ETO. Right.
Yeah.
So you are right, sir, that you are already getting the value ET naught. So you have
Yeah.
information of
Yeah.
ET naught, that is reference crop evapotranspiration, and you are
Yeah.
getting a value of around 5 mm per day.
Yeah.
And you should also see the thing that mm per day, but it has been taken as an average value for a month. Okay.
Right.
Now, what is they are asking? They want to know the actual evapotranspiration. As you already, as you just mentioned, sir, you can
Yes.
see that there has been a certain kind of fixed crop we have selected. Okay, so there has already some kind of standardization have been made, okay, into this, like
Right.
grass, whatever the grass they have picking, having a height of, you told na 8, how much, sir, you told?
I think 8 to 15 centimeters, sir, if I
Yeah,
remember right. Yeah.
8 to 15
Yes.
centimeter, yes, you are right.
Yeah.
So 8
Yeah.
to 15 centimeters. So uh, what is your observation, like if, while when we are going into the field, do we get 8 to 15 centimeter of grass everywhere?
No, so of course not. It depends on
Yeah,
the crop, the type of crop,
exactly,
and
yes,
yeah, maybe the size of the leaves, and what is the height. And also, I understand it depends on which phase of the growth of the crop also
yes,
makes a difference.
exactly.
Yeah.
So definitely for computing this, we should have some certain kind of correction we should make in this while computing the actual evapotranspiration, right?
Right. Right.
Okay. Now take a certain kind of correction values they have given. So crop coefficient they have given, noted down 1.2, soil coefficient they have mentioned 0.8. And now let's see some kind of discussion. Okay,
Yeah.
so you can see that if we are summing up the transpiration as well as the evaporation in the region, we are getting the
Mm.
evapotranspiration value, right?
Yeah.
Now, this ET value will depend on factors like type of soil,
Yeah.
crop, what is being sown in the soil. Okay, and for
Yeah.
this, you can see this picture, this both the pictures, or
Yeah.
maybe you can see again. Firstly, you can see this picture, first one. I am just highlighting as first. So there is a certain kind of climate is there, okay, occurring over a over a like a reference crop they have selected, okay.
Mm.
So yes, for your information, I just want to add, yes, sir,
Yeah.
whatever the things you mentioned, it is have been mentioned here also. So
Yeah.
reference surface they are considering of 8 to 15 centimeter of healthy growing green grass, and
Right.
also the thing is shading comparatively or entirely in the region over a dry
Right.
soil surface. So
Right.
now you can see that we are having the grass reference crop and we are directly getting the value ET naught. Okay.
Mm.
Now what we are doing, we are correcting this ET naught value by multiplying Kc. What is Kc? Kc is a crop coefficient, right? And
Correct.
how it is varying? This Kc value, it is getting varying also, like it is varying with the like growth of the plant. Okay. So yeah, now you can see that if we are at the initial stage of plant growth, then crop coefficient is in between 0.2 to 0.4, it is taking like that, but come up with to this. So here initial period, if we are having an initial period, so planting to 10% ground cover, here whatever the plant growth is going, it is covering of around 10% growth only, 10% growth is there. Now as we move further, crop development will be there, and it will now have flowering also. So for this case crop development, so we should have value ranging from maybe you can say 0.3 to up to say you can say 1, we come up with one value. So Kc we can also, it will range between 0.2 to 1. Okay, so likewise we have to select the Kc value from this. Also you should see that we also look in the soil part, right? How the soil present in that region. Why I'm saying this is that you can see the difference. Okay, because if we are having a clay soil, okay, before going to this, can you tell me which soil will contain more moisture, clay or sandy?
Clay.
Ah,
That's good.
yeah,
Yes. So clay will be storing more water, right? And
correct.
also clay have ability to what? Water holding ability or water draining ability? Can you tell me?
Holding.
Yes, right, right.
Yeah.
So water
Mm.
holding ability is more as compared to sandy soil. So based on this, AET upon PET ratio, this is a ratio, that is a factor. So
Mm.
it is having a variation with the presence of moisture in that in the soil layer. So maybe soil layer may be saturated up to field capacity, maybe at a time, or maybe having a permanent wilting point where the plant is not able to extract the water now. So
Mm.
based on this, we have to select the Ks value, that is a soil coefficient.
Mm.
So this is important. Now I also want to mention one thing, that whatever the reference crop have been it have been demonstrated or we are selecting, it is given by the FAO. That is, can you tell me the full name of this?
Oh. Food. What is that?
Yeah, yeah, yes, yes.
Food assurance. What is that?
Agriculture
Sorry,
organization.
organization. Some
Yes,
organization.
yes,
Yeah.
yes, right.
Mm. Yeah.
So basically they have just recommended to use certain kind of reference, and then we are computing this. So now we have to proceed for the solution.
Yes, sir. So we multiply both the factors with that 5 per day.
Yes, yes.
Yeah.
So what could be the
Sir, I
answer?
just wanted to
Yeah,
check with you.
yeah,
So, if the green area, the leaf area increases and it is more green,
yeah,
can we just say that the evapotranspiration will go up and the crop factor will correspondingly increase
yeah,
during
yeah,
the
yeah,
life
of
of the
course,
crop?
yes. Now the
But during
flowers are more.
harvest,
Yeah,
the leaves will turn more brown, right? Even though the leaf area might be high, but because they turn more brown, it is that then the evapotranspiration, the Kc is going down because of that. Like
which one? Brown, I'm
during
not.
harvest, just before, if you see the right side of your
Yeah,
picture,
yes, yes,
Kc is again going down during the harvest phase, right? The last part,
yes,
like
yes.
late season.
So
Okay.
basically at this time, whenever we are coming up to harvesting, so
Hmm.
you know that the plant leaves which are holding the moisture, they
Hmm.
already gone up, like it is
Yeah.
getting reduced now. Okay,
Okay.
so
Okay.
that is
Okay.
why we are considering lower value as compared to
Yeah.
what have been in the, yeah,
Yeah. And one last thing, sir, the Ks, variation of Ks with the crop season,
yeah,
the phase of the crop won't be there, right? As long as it is clay and it is watered with I mean, whatever is the recommended, what it's saturated, for example, then Ks can be assumed to be constant during the entire phase of the crop.
uh, what can you repeat it?
No,
Yeah,
sorry. Now, Kc, you have shown a profile how Kc
yeah,
varies over the
yes,
life of the crop.
right.
But similarly, Ks, variation of Ks would be there. Similarly,
uh, not mandatory, like it is, I don't think it should be varying in that manner, because what I'm just observing is that the thing is, like, we are watering the soil, right? We have to
right?
continuously provide the moisture.
Correct.
So we like as a part of soil expert, or maybe from an agricultural background person, he can definitely say that
Yeah.
yes, he is knowing the frequency based on which water should be given to the plants, right?
Correct.
So
Correct.
definitely fixed amount of moisture will be always, like, it will always be maintained in the soil. Okay, it
Correct.
is not getting reduced now, because if it is
So,
reduced, then definitely a plant is not growing now, right?
yeah, yeah.
So I
So
guess,
Ks should remain constant, is what
yes,
you're
yes,
saying,
yes,
right? Yeah.
right, yeah.
Okay. Right. Thank you.
Okay, so Ashish, getting the things or not?
Yeah, I'm getting it.
Okay, so 4.8, right? So it is in per day, right? So what were the values we are getting? So it was 5 So we have to just multiply 1.2 into 0.8. we are multiplying it with 5. How much value you are getting?
4.8.
Yeah, 4.8, 0.8, sorry, 0.8 into 5. Yes, I am also getting 4.8. So 4.8 mm per day. Okay, I am moving to next question. So the question here is, Penman evapotranspiration equation is based on. Now it is want to know the, like, how we come up with the Penman evapotranspiration, like ET equation, how we come up. So what are the methods we have considered in order to come up to Penman ET equation?
So, from my understanding, it's both the energy balance and the mass transfer approach.
Yeah, Ashish?
Yes, correct.
Okay, that's good. Can you tell me status of Bala Murugan?
Just give me one. Yeah, he is replying. Fourth answer is correct.
Ah, that's good. Yeah, good. Okay, so we already go through energy balance method, right? At the same
Yeah.
time, this mass transfer is nothing but an aerodynamic method we studied in the earlier section. Okay, and water budget method we also studied, that is water budget is nothing, it is the mass balance. Okay, input minus output equal to storage. So for your like further information, so Penman equation is based on combination of both energy balance and mass transfer approach. Now the thing one I want to just mention, okay, firstly look at this. So Penman method, so this is just a simple expression for computing the evapotranspiration value using Penman model. Okay, so what are the parameters we are using? It is directly, you can see here. So it requires firstly a wind speed. Okay, so we need like U2, you can see. So it is just a wind speed, and then you can see ES. So ES is nothing, it is just a vapor pressure of moist air
Yeah.
at
Saturated vapor
yeah,
pressure.
right, saturated. And EA is just an actual, right?
Yeah.
Yes. Okay, so I want to just mention one more thing, that adding to both energy balance method and mass transfer method, we can derive both. Like, one is Priestley-Taylor method, you already know Priestley-Taylor method, and the another one is Penman-Montet. Penman equation you can also compute. Okay, certain kind of assumptions are there, but I want to sorry, Penman-Montet, it is Montet. Okay, so I just want to mention one important difference between these two methods. What is this? That for Priestley-Taylor equation we require minimum data, right? Minimum data is required, like what data they need, that is just a weather data, net radiation and mean air temperature. Using both these input parameter we can directly get the ET value. Okay, ET value in the region. But if we are preferring Penman equation, okay, in order to compute ET value, so what it extra requires? So it extra requires a daily data. You can see we know that getting a like finer scale of data, like, okay, finer scale of temporal data, like for example here it is asking about humidity. Okay, also it is asking about the wind. So it is basically a little bit tedious. Okay, not everywhere you can get this daily scale of data. Maybe you can get average of 10 days, or maybe of 8 days. Usually people record like this. So like apart from this, like apart from the two parameters, it also requires daily data for humidity as well as the wind. So this is why people used to prefer Priestley-Taylor method for computing ET more in comparison to Penman model.
Okay.
Yeah. Now coming to the next question. So it is again a question based on evaporation pan. Okay. So evaporation pan have been installed near the bank of reservoir, you can say. Okay, and what this evaporation pan is, it is an IS standard class A pan, you can say. Okay, now they have this water surface area. Water surface area means what? That is AS. They are showing that you are having 100 hectare of land you have. So you can consider a certain kind of reservoir in the sense, if we are considering this is a certain kind of gravity dam. Okay, and now if we are looking for the water which have been stored in this particular stretch. Okay, so how we can compute? Okay, so this particular area, there is continuous evaporation is going on. Okay, and we want to compute the evaporation value, that how much evaporation have been done, and based on that we want to adopt certain kind of inhibitor, maybe evaporation inhibitor that we discussed, cetyl alcohol.
Yeah.
Okay, we want to
Yeah.
spread it. So how much we have to come up, and we have to decide that yes, evaporation is significant in this particular season, and at this particular location, so definitely we have to do. Okay,
Yeah.
so the thing is there. So we want to compute the anticipated evaporation loss from the from the reservoir, and unit will be what? It is asking in meter cube per day. Okay.
Yeah.
So
So,
any
sir, 1 hectare is about 10,000, is 10,000 square meters.
yeah,
Uh,
100 into 10 to the power 4
4.
meter
Yeah.
square. Yeah.
Yeah. So
Yes.
100 into, so 1 into 10 to the power of 6
6. Yeah. Yes.
meter square.
Right.
And then pan is 0.04 meter per day. Uh,
Yes.
the
Per
day,
day.
and the pan coefficient, like you guided us, was zero point 0.7 for a ISI pan.
Yes, zero point
Right.
0.7 to 0.8, but you can say, you can take any value, like ranging from 0.7 till it is specifically mentioned in your question. If it is mentioned, then you have to take, right, that
Okay.
value. Yeah.
Yeah. So here, yeah, sorry, I'm just doing a very rough calculation. I'm
Yes.
getting some 28,000 cubic meters per day. I don't know. Can my our friends just check it out?
Yes. Yes.
It's
Yes.
just a rough.
Ashish,
Okay.
any input from your side?
Yeah, I'm calculating it. Just give me 1 minute.
Good. Good. I'm waiting for a minute. Okay.
So we take
Calculate it.
100 into 10 to the power 4 into 0.04 into
Okay, Bala Murugan already replied. He's saying 28,000 cubic meter per day. Okay, good. Sorry.
yeah, 28,000.
That's good. Wait a minute. Okay. So was it
Oh,
clear? Okay,
yeah.
not a
So if you
deviation.
take
Okay.
point 0.8, then you get
Yes, not an
32,000.
issue. Okay, if it is not an issue, because
Okay.
yes, I mentioned that if it is not given in the question, you have to take value ranging between 0.7 to 0.8. You have to take
Okay.
for
Okay.
IS class A pen. So
Okay.
your answer is correct, not in between. Okay, I'm
Okay.
moving ahead.
Sure.
Yeah. Now the next question is related to evaporation rate. Okay, which we have to compute using energy balance method. Okay, so till now we have only discussed about the methods, that what are the methods we have, like experimental method, analytical method, empirical method. Now we have to deal a numerical problem related to energy balance method, like how we are getting the evaporation rate using this method. So we
Yeah.
need to compute ER, okay, energy balance method, and for that we have input data, like firstly you can see,
Net radiation.
yes, Rn we have been provided. So Rn, you can see this is 350 Weber per meter square. Weber per meter square is a unit. Okay, not a Weber, I guess it should be a watt.
What per meter?
Watt per
Right,
meter
yeah.
square.
So it will be a watt per meter square, and then it is saying that water surface temperature, it is mentioned in the question. It is saying 45 degrees Celsius, and at the same time it is mentioning that density of the water you have to take is 1000 kg per meter cube, right? Now can you tell me like any like you may be knowing the formula directly, like after deriving the energy balance method using continuity equation, and as well as the energy conservation principle.
Yeah.
Okay.
So it is the radiation divided by the density of water, and also, I mean, divided also by the latent heat of vaporization,
Yeah.
which is to be calculated using this temperature, which
Right,
is,
right, right.
yeah.
It is dependent on temperature. You're right.
And that is
Okay.
an empirical formula, I
Yeah,
think. Yeah.
exactly.
Yeah.
Uh, it is an basically it is an analytical. Why I'm just
Okay.
saying, because this formula is have been derived using uh, Reynolds transport theorem. Do you know this?
Oh, yeah, yeah, of course.
Yeah,
Is
so
it?
using
Yeah.
using the concept of Reynolds transport theorem, while the our system is at continuity, as well as the energy is being conserved in the entire system. So based on that, this entire formula have been come up. Now I want to add one more thing, that this Rn is always having certain kind of additional terms, that is there is one more term, that is heat, sensible heat, and there is one more term, that is G. That is G in the sense what? That is how much water, how much radiation is going into the surface. Like you can see, if it is we are having a hydrologic system, and we have the water level like this, and we know that this is the ground. So this Hs amount of heat is going beneath the ground, and sorry, this will be a G, and whatever the Hs is going, this is an out like sensible heat going out of the system, and Rn is the net radiation which is getting stored in this entire hydrologic system. Okay, so based on this we have to compute. So using this formula, can anyone say that how much value we will be getting? Keep in mind that LV we have to compute. LV is there. There is one more relation. Okay, empirical relation is there for computing the latent heat of vaporization. Okay. So yes, you can see. Hello. Hello.
Yes, yes, yes.
Okay, okay, good, no issue. So you can see the input that have been provided in this question. So net radiation we have a sorry, this is not an air temperature, I guess, or maybe yeah, of course it will be an air temperature over the water surface. So yeah, you are right. It will be 45 degrees Celsius. Then sensible heat we are considering here, it is 0, because it has been already mentioned that we have to assume Hs is 0. Groundwater heat flux we have to also assume it as 0. Density have been
Yeah.
given, and then this is a formula.
Yeah.
Now for computing the LV, you have to see this empirical relation. So using this, you have to compute the latent heat of vaporization. Ashish,
Hmm.
compute this and try to match whether we are getting this value or not.
P we have to put in degree centigrade, na?
Yeah, right. Yes.
Yes. It says one decimal place, so it should be 11.6. Oh, I'm
Okay,
getting
you are getting
11.5.
direct value. Okay, that's good.
Yeah.
Good,
Yeah.
good. So you got the value directly. ER.
Yeah.
Good. Ashish, try
Yeah,
to
this is
solve it.
okay. 2.394 is okay.
Ah, that's good. And what about this ER value?
Yeah, this is 1.33 10 to the power minus 7.
Ah,
Correct.
that's good. Now you have to convert it in mm per day.
Yeah.
Okay, okay. This is 10 to the 6. We have to. Okay, got it.
Okay. Ah, that's good. Okay, Bala Murugan, I'm satisfied with your answer. Good. Okay.
So
Now
this
I'm.
LVs, whatever that equation to calculate LV, it
Yeah.
looks like an empirical formula because of numbers like
Yeah. I
2.501 and
just mentioned
23.
yes, yes, yes.
Oh,
Right.
oh, sorry, I missed that. Yeah.
It is an empirical relation.
Okay.
So based on the experiments, it have been derived.
Okay.
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 Yeah.
Yeah. Sure. Thank you.
Okay. Now we again have a question, but from my opinion, this is a good question because uh, while we were in our meteorological observatory in our department, we were having this task to compute evaporation. Okay, and we as I just shown you one picture that in our department itself we have class A pan. Okay, so we were told like I was measuring the data during monsoon period and I faced this particular problem. Okay, that how during a monsoon period how we will calculate the ET value. Okay,
Hmm.
how we will be computing sorry ET, not a ET value, it is an evaporation value, so only E. Yes,
Yeah.
so the task was like if we are having a water body of area, it is mentioned directly a 3000 hectare. Okay, so directly it will be 3000
To
into 10
10
to the
power
power
4.
4 meter squared, right?
Yeah.
And now what have been done, like what is the meaning of entire question? So now it is saying that for the entire day, like this evaporation, keep in mind, for evaporation we have to measure the reading at 5:30 p.m. We have to
Okay.
make the reading at the evening. Firstly, we will what we will do while we are just going in the observatory for installing the graph in recording type of grain gauge. We also make adjustment in the pan. What we do, just I want to mention one thing. That is one more like it is an interesting thing to see. Wait a minute. Yeah, you can see this is a class A pen. Okay, so there is certain kind of circular cylinder is there, and inside this circular cylinder there is there is a tip installed in this. So at while entering into the this observatory, what we have to do, we have to fill this entire class A pan up to this point at the top till this point touches the water surface. Now we will leave it. We will leave it till 5:30. Okay.
Okay.
Now at the 5:30 we will again go into the observatory and we will try to figure out that how much depth of water have been gone down. Like once, if I say this is a column, right? Assume it is as a column. So once we have fixed it, this is one this was an tip. So we have fixed this water up to this, and now due to heat energy it have been observed, so water have been evaporated and now the water level have come down up to this. Okay,
Yeah.
so this is a final df value, we will say. So this was the case. Now come to the question now. Yeah. Okay. So what it is saying, that quantity of water added to bring the water surface in the evaporation pan to stipulated level is 11 meters. So how much water we have added? So we have added uh, because we are measuring the data at 5:30, so we got the difference, like we got the reduced water level, and at that time to make it normal, what we did, because at the night definitely there won't be any kind of sunlight will be available and no evaporation will be there, so we used to fill this entire class A pan, and for filling this we need volume how much, 11 liters of water.
11-liter volume.
Okay, now we have to see if it is like I will say this is a circular kind of evaporation pan, so it will be having an area, right? And for this case dia has been also provided, you can see
Yeah.
122 centimeter,
Mhm.
and pan coefficient is also given 0.7. And one more thing, in the similar way, near this class A pan there is a rain gauge station have been also installed. And what it is recording? It is recording that 7 mm of rainfall have also been received in the day. Okay.
Hmm.
Now the two things are happening. Evaporation is also happening and rainfall is also coming. Now we have to compute. So yes, this is a real kind of problem I faced during that time. So
Okay.
what we will do first, as at 5:30 when we are just adding the water, so we are just adding the volume, right? So volume will be what? That is the area into depth of water, right?
Mhm.
Depth of water. So try to compute the depth of water which have been added to this. Firstly compute this. So it will be a volume divided by area, and you know that this is a circular pan, circular class A pan. So definitely it will be having a area of pi by 4 into
D
d
square.
square. So you have to compute the area in that manner. And keep in mind, try to convert this value also, 11 liters. It should be, try to convert it in meter cube. So what we have to do, you have to multiply it with 10 to the power minus 3 meter cube. It will be like this.
Correct. Correct.
And let me know the depth.
So it's like doing a mass balance equation on the pan first. Yeah.
Yes, exactly.
Yeah.
That how much water we are
Yeah.
just adding into it.
Right.
So we will have idea that yes, within a day, water rainfall have been there. Okay. So
Yeah.
definitely this 7 mm of rainfall water,
Yeah.
it has also been come up in this evaporation pan also, right?
Correct. Yes.
So whatever the value depth of water we are getting, so
Hmm.
this will be the thing, and at the same time we have to add up that
The
precipitation,
rain.
that rainfall
Yeah.
value.
Yeah.
Okay, and then we will get that total evaporation, that how much it have been occurred in the class A pan.
Yeah. So, sir, the net water loss, that means, I mean, precipitation is also part of that. I'm
Yes.
getting around 9.41 millimeters. And if I add that 7 mm rainfall, I'm getting the evaporation as some 16.41
Okay,
millimeters.
16.41. How much mm? Mm or
MM, please.
centimeters?
Please. MM.
Okay, mm. Good. Ashish, any kind of uh,
1 minute.
okay. Okay. So this is just a input
Yeah, only an input.
listed
Yeah.
here. So area of the water body, it is mentioned here. Water added to the pan, it is there, and it has been converted into meter cube. Then again rainfall measured from the rain gauge, it is coming up to 7 mm, and then diameter also been provided, and can pan coefficient we have.
Divided by, okay, 11 divided by 1.168. So 9.41 into 10 to the power minus 3 is the meter
Okay,
depth.
what is the unit? Like depth you are getting? How much?
Yes.
9
It's
point
9.4 mm, you can say.
9.4 mm. Okay, that's good. Then again, now you have to add up that
Rainfall.
rainfall value.
Yeah.
So let's see. Yeah, you are right that total water added in the pan. So this is a depth. So it is saying that it is coming up to 9.41 mm.
Hmm. So
Okay.
6.41 is correct. Yeah.
Yeah. So once we are adding the rainfall, okay, which have been occurred in the class A pan itself. So we are coming up to 16.41 mm. Okay.
Mhm.
And now what is the task? So task is that they want to know that evaporation from the water body in this unit they are asking. So that they are asking in volume. Okay. So they want to know the volume of water or total volume of water which have been evaporated from this pan.
Million meter cube. Okay.
Yeah.
Million meter cube. Yeah.
So million meter cube is nothing. It is just a 10 to the power 6 meter cube.
Hmm.
It is like
Yeah.
this.
16.41 into 0.7 into,
Don't forget to multiply coefficient also.
yes,
Okay.
yes,
Yes,
yes.
yes,
Because it is
yes.
important.
And then area is 30. How much area?
3 into 10 to the power of 7 meters square. I'm getting around 0.34 million meter cube.
Yeah,
Okay.
you are right. Yes, of course, sir. You are right. So it is 0.34 million meter cube. I'm just waiting for other people also. Let's see whether Balamurgan replied or not. Okay, Balamurgan, you got 11.6. Which one? Yes, 16 mm. Ah, that's good. Good. And now you have to calculate the total volume of water which have been evaporated from the pan.
Can you show me the area for the
Yeah,
previous
it
slide?
is 3000 hectare.
Okay, okay.
Yeah.
3000 and 21, 24. So, 1, 2, 3, 6. So I'm getting 3. I have to divide by 10 to the power 6 to get million meter cube.
Yeah.
No,
Yes, yes,
10 to
yes.
the power 9, I think. 10 to the power 9.
How much?
I have to divide it at first 10 to the power 6, then
Oh.
10 to the power 3 to
Yeah.
bring it into the million meter cube. Yeah,
Ha
correct.
ha ha. Then how much you are getting? Final value.
0.344
Ha
million meter
ha.
cube.
Good, good. No issue. Okay, I'm moving ahead. Okay. So there is one question related to isoplinth. So it is asking that what you understand by isoplinth. Okay. In earlier classes, we also discuss one of the like there was one word that is
ISO height.
isohytal, right?
Height.
ISO height.
Mm.
Yeah.
Yes, isohytal was there. Then we also discussed that isobar are also there.
Hmm.
Okay, sometimes we used to call isotherm, right?
Temperature.
So they have they all are kind of contours only. Okay, now this time we are dealing with isoplinth. So you have to tell which option is right. So it is saying that mean annual PET. PET is potential evapotranspiration.
Which number third? I think number third is correct.
Okay, number third. Yeah, you are right. So number third is correct. So I will be discussing more details in this. So you are right that isoplates are the line on the map through places where we are making a plot of equal depth of evapotranspiration. So from the picture you can say this is an map from India. Okay, I took this map from scientific report which is there from Meteorological Department, IMD. So you can see there are lines. I will um, like I
So, but
want
this
to.
can only be ETO, right? Because crop and everything might be different, soil might be. So, we are only talking of ETO when
Yes,
we
yes,
talk
yes,
of
yes.
isoplates. Yeah.
Reference is ETO only. Yeah.
Okay.
Yes. So this is a contour. Okay. Now this entire contour, it is saying that for this entire region of Hyderabad, it is having a PET of about 180, 180 centimeter. Okay. But if we talk about the PET in case of Rajasthan area, okay, so you can see the similar kind of trend is also existing here, 180 centimeter. But I want you to tell me that where PET is high, in which location of the India we are getting the higher PET value.
In Saurashtra? Oh,
Yes, 200 something.
yeah. Hmm.
So PET basically it has more association with the humidity. Okay,
Mm.
humidity plays a significant role in while we are dealing with the
Yeah.
evapotranspiration in the region, right? So in case of
Even near
Gujarat,
Chennai, for example, it's 200.
yes, of course, it is a coastal area. Humidity will
Yeah.
be, you will receive
Yeah.
more humidity in this, right? But as compared to like in our Uttarakhand, you can see humidity is of about 120 only. Sorry,
Mm.
it is about 120. So definitely humidity will be low.
Yeah.
Now there is one last question I say. It is asking that when the moisture content in the catchment is at field capacity, okay, which condition will be true? So AET is what? This is an actual evapotranspiration. PET is what? This is a potential
Potential.
evapotranspiration. So potential transpiration is just like a similar to reference crop evapotranspiration, because there is a certain kind of reference we are taking. We are assuming that PET will occur where the grass is fully like it is having a water of about maybe up to field capacity. Sorry, it may take a water significant amount of water. It is enriched in water area. This is the scene, but actual will be a field based scenario where correction may be there related to coefficient of crop we are dealing with, soil we are dealing with. So AET will be different. Now you
Then
have to,
AET is equal to PET.
Yeah. It should be
yes,
equal in this case. Yeah.
right. So we will look into this picture. We can directly get that what we want to get the value. So we are talking about a field capacity. So if we are here, if we are having at this point, so we will be getting the value of percentage ratio of something 100%. Okay, we
Mm.
are getting up to here. So definitely AET upon PET is 100%, so it will be equal only, right?
Right.
So there is further information that at field capacity in the soil layer, AET is equal to PET. At permanent wilting point, you will be getting this ratio,
Yeah.
AET upon PET equal to 0, which was there
Yes.
in one of the options, right?
Yeah.
Okay, so this is what we discussed in this
Question,
session now.
a general question, if it's okay.
Yeah,
If you have a lysimeter and you have the Penman-Monteith uh, equation, which is a empirical method,
yeah.
and you have a lysimeter, generally, what is the difference in their readings? Like the calculated value, it would be less than 5%, or it you can't say it just offhand. Like,
Can you repeat once again, sir? Yeah,
see, a Penman-Monteith method is
right.
like an empirical method,
Yes.
and the lysimeter makes a actual measurement for evapotranspiration,
Okay.
right?
Yeah.
So generally, there have been found any studies that how close one is to the other one in terms
Okay.
of yeah.
Yes. So basically, I want to just mention that whatever the empirical method we are preferring,
Yeah.
so like from my opinion,
Yeah.
uh, empirical methods give higher values as compared to
Oh.
what we are getting in the while we are performing the experimental setup. It is not
Okay.
necessarily that we are getting the accurate. Yeah, definitely there will be a deviation, like we will be getting maybe lower value in case while we are measuring through the lysimeter, but we
Okay.
have to assume, we have to take the confidence, the data which have been acquired while we are using the lysimeter, because this is a
Okay.
directly based on field measurement.
Hmm.
So we will prefer this.
Okay. Okay, sir.
So difference will be there, of course
Okay.
you are right, but
Okay.
values will be higher in case of empirical, because empirical methods, whenever they used to experiment, so basically they acquire a large area, okay, and
Okay.
they have to average it out the certain kind of coefficient values,
Okay.
okay. So based
Hmm.
on that they are getting higher values as compared to what we are getting in the field.
Okay.
Yeah.
Thank you. Thank you.
Yeah. So any more questions to discuss? Yeah, lysimeter gives actual crop evaporation. Okay. Yes. Difference is crop coefficient. Yeah. Yeah, coefficient is there. Yeah, definitely. That is why. You're right. So should I stop presentation?
Yes,
Uh,
yes, yes.
Yeah.
we will meet in the next session. Okay.
Yes, sir. Thank you so very much. Thank you.
Yeah.
Yeah.
Thank
Okay.
you.
Thank you so much.
Yeah.
Thank you,
Thank you.
Ashish. Thank you, sir.
Yeah.
Thank you,
Thank
Bala
you.
Murugan. Okay. Yeah.
Bye.
Bye.
Right.